At the deepest levels of inquiry, a troubling pattern begins to emerge. The mathematical frameworks we rely on to describe reality with the greatest precision consistently lead to conclusions that feel profoundly at odds with our most ingrained intuitions about how the world should behave. Instead of reinforcing familiar ideas about causation, locality, and stable existence, precise measurement reveals results that quietly undermine them. The more accurately we probe reality, the more the equations suggest that the assumptions making measurement feel meaningful in the first place may not hold in the way we instinctively expect. You're sitting in your room right now, surrounded by objects that appear solid, permanent, and separate from each other. The chair beneath you feels substantial. The walls around you seem to mark clear boundaries between inside and outside. Time flows forward in a steady, predictable rhythm. These aren't philosophical beliefs you've chosen to adopt. They're the direct testimony of your senses, refined by millions of years of evolution to help you navigate a world where objects have definite locations, where causes precede effects, and where things either exist or they don't. But here's what makes the night feel a little colder. When physicists measure the world at its most fundamental level, when they peer into the quantum realm that underlies everything you see and touch, the mathematics tells a completely different story. Not just a slightly different story, but one so removed from everyday experience that even the scientists who work with these equations daily acknowledge the difficulty of interpreting what the mathematics is implying about the nature of reality. The equations work. They work with a precision that is difficult to overstate. Every prediction quantum mechanics has made about the behavior of particles, fields, and forces has been confirmed by experiment after experiment, often to more than 10 decimal places. The technology in your phone, the GPS satellites orbiting overhead, the MRI machines in hospitals, the lasers scanning barcodes at grocery stores. All of this depends on the mathematical framework of quantum mechanics being not just approximately correct, but extraordinarily precise. And yet, when you try to translate what the mathematics actually says about reality into plain language, into concepts that make sense to a human mind, something feels strained. The translation doesn't just become difficult, it becomes extraordinarily challenging without questioning fundamental assumptions about the nature of existence itself. And that's where things quietly become uncomfortable. Consider what happens when we try to answer the simplest possible question about a quantum particle. Where is it? Classical physics, the physics of our everyday experience, suggests this should be straightforward. An object has a location. It's either here or there. You might not know where it is, but it definitely has a definite position somewhere in space. Quantum mechanics says something very different. Not that you can't know where the particle is, not that it's moving too fast to pin down. The mathematics indicates that the particle does not have a definite location until something measures it. Before measurement, the particle exists in what physicists call a superposition of all possible locations weighted by probability. It's not that the particle is somewhere, and we don't know where. According to the mathematics, it's described as existing across all possible locations simultaneously. This isn't a limitation of our instruments or a gap in our knowledge that future technology might fill. The mathematics of quantum mechanics is built on the foundation that this indefiniteness is fundamental to the theory itself. The particle doesn't have a location in the same way that the question, what's north of the North Pole, doesn't have an answer. The question itself assumes something about reality that the theory does not support. When you first encounter this, the natural response is to assume it must be a metaphor, a convenient way of talking about something more familiar underneath. Surely the particle really does have a definite location, and quantum mechanics is just the best approximation we can manage with limited information. This was Einstein's position. He famously insisted that God does not play dice with the universe, arguing that quantum mechanics must be incomplete, that there must be hidden variables determining where particles really are, variables we simply haven't discovered yet. But in 1964, physicist John Bell proved mathematically that this intuitive picture cannot be sustained under certain assumptions. Bell's theorem shows that if particles had definite properties before measurement, if they carried hidden information about where they are and how they behave, then certain combinations of measurements would have to satisfy specific mathematical inequalities. When experimenters actually performed those measurements, the inequalities were violated consistently, repeatedly. The hidden variable picture isn't just unsupported, it appears incompatible with experimental results under those assumptions. This leaves us in a strange position. The mathematics indicates that reality, at its most fundamental level, doesn't align with our deepest intuitions about how things should work. And the mathematics has proven extraordinarily reliable in its predictions. The strangeness doesn't stop with individual particles. When two quantum particles interact, they can become what physicists call entangled. The mathematics shows that measuring one particle produces correlations with the other, regardless of how far apart they are. Not that information travels between them at the speed of light, not that they were coordinated before they separated. The mathematics describes correlations that do not depend on spatial separation. Einstein called this spooky action at a distance and argued it suggested quantum mechanics might be fundamentally incomplete. How could measuring a particle here be correlated with a particle on the other side of the galaxy? It appears to challenge everything we know about causality, about the speed of light as a cosmic speed limit, about the basic structure of space and time. Yet experiment after experiment has confirmed that entangled particles do exhibit these unexpected correlations. In 2022, the Nobel Prize in Physics was awarded to 3 scientists who provided definitive experimental confirmation of quantum entanglement, closing the last remaining loopholes in the experimental tests. The universe does exhibit these correlations across arbitrary distances. What makes this particularly unsettling is that we're not talking about exotic phenomena that only show up in billion-dollar particle accelerators. Quantum entanglement occurs naturally in biological systems. There's evidence that it plays a role in photosynthesis, in bird navigation, and possibly in the neural processes underlying consciousness itself. The same mathematics that predicts non-intuitive correlations between particles separated by light years also governs the molecular processes happening inside your brain as you read these words. The measurement problem goes even deeper. In quantum mechanics, the act of observation doesn't just reveal information about a particle's properties. According to the mathematics, observation is associated with the particle acquiring definite properties it did not previously possess within the theory. The transition from indefinite superposition to definite measurement outcome is described as occurring at the moment of measurement. This is called the collapse of the wave function, and there is no consensus on how to interpret it. The mathematics describes the superposition beautifully and predicts measurement outcomes with perfect accuracy, but it provides no agreed-upon mechanism for the transition between these two states. It's as if the equations work perfectly for describing how reality behaves, before and after measurement, but remains silent about the moment when indefinite possibility becomes definite actuality. Some physicists have proposed that consciousness plays a special role in collapsing the wave function, that the universe remains in superposition until a conscious observer makes a measurement. Others suggest that every possible measurement outcome occurs, but in separate parallel universes that branch off from each other with every quantum event. Still others argue that the wave function never actually collapses, and that our impression of definite outcomes emerges from deeper quantum processes. None of these interpretations enjoys universal acceptance. Each one requires reconsidering some fundamental assumption about reality that seems deeply rooted in everyday experience. Either consciousness plays an unusually direct role in physical processes, or an enormous number of parallel universes exist, or our most direct experiences of definite outcomes are emergent rather than fundamental. Every interpretation of quantum mechanics asks us to engage with ideas that strain our intuitions about the nature of existence. The strange thing is that this disconnect between mathematics and intuition isn't limited to quantum mechanics. General relativity, Einstein's theory of gravity, makes predictions that are equally removed from everyday experience. The theory says that massive objects bend the fabric of space and time itself, not that they create forces that pull on other objects through space. The mathematics describes space and time as physical entities that can be stretched, compressed, and curved. According to general relativity, when you're standing on Earth, you're not being pulled downward by gravity. You're following the straightest possible path through curved space-time. The curvature created by Earth's mass means that straight in your local region of space-time points toward the center of the planet. You experience this as weight, as being pressed against the ground, but the mathematics describes this as motion through curved geometry. Time itself becomes flexible in general relativity. The theory predicts that time passes more slowly in stronger gravitational fields, and more slowly for objects moving at high speeds relative to an observer. These aren't just tiny theoretical effects. GPS satellites have to correct for time dilation effects predicted by relativity, or they would accumulate errors that would make navigation impossible within hours. The mathematics has been tested in every conceivable way. Physicists have measured time dilation effects using atomic clocks on airplanes, confirmed the bending of light by massive objects during solar eclipses, detected gravitational waves from colliding black holes billions of light years away. Every prediction of general relativity has been confirmed with extraordinary precision. Yet when you try to visualize what the mathematics actually describes, something in your mind rebels. How can space and time be things that bend and stretch? How can the passage of time depend on where you are and how fast you're moving? How can effects we call gravitational be geometric rather than dynamic? The mathematics is precise and predictive, but translating it into concepts that feel comprehensible often requires reframing basic assumptions about the nature of space, time, and causality. Perhaps most unsettling of all is what happens when you try to combine quantum mechanics and general relativity. Both theories work perfectly within their own domains. Quantum mechanics describes the behavior of particles, atoms, and molecules with incredible accuracy. General relativity explains the motion of planets, stars, and galaxies with equal precision. But when physicists try to apply both theories simultaneously to situations where quantum effects and gravitational effects should both be important, the mathematics ceases to produce well-defined results. The equations produce infinite answers to finite questions. They predict that the curvature of spacetime should become infinite at the center of black holes and at the moment of the Big Bang. They suggest that the quantum vacuum, the supposedly empty space between particles, should contain an enormous amount of energy. These infinities aren't just mathematical inconveniences. They mark regimes where our most successful theories are no longer sufficient. For nearly a century, physicists have been trying to develop a theory of quantum gravity that would resolve these infinities and provide a unified description of reality at the most fundamental level. String theory, loop quantum gravity, causal set theory, asymptotic safety. Dozens of approaches have been explored, each requiring mathematical concepts so abstract that they can barely be expressed in ordinary language. Some of these approaches suggest that space and time themselves might be emergent properties of something more fundamental, that at the deepest level, reality might consist of pure information or abstract mathematical relationships, or discrete building blocks so small that the very concepts of location and duration lose their meaning. Others propose that we live in a holographic universe, where all the information in a three-dimensional volume is actually encoded on its two-dimensional boundary, like a cosmic hologram. If you pause and really sit with this, the implications become intellectually disorienting. The mathematics that governs reality consistently points toward conclusions that feel difficult to reconcile with everyday experience, particles that don't have definite properties until measured, correlations across cosmic distances, space and time that can be bent and stretched like physical materials, vast energies associated with empty space, information that may be as fundamental as matter and energy themselves. None of these ideas emerge from philosophical speculation or mystical intuition. They're the direct mathematical consequences of our most successful theories of reality, theories that have demonstrated extraordinary, predictive success. This creates a profound puzzle about the relationship between mathematics and reality. Why should the mathematical structures that describe the universe be so different from the way reality appears to conscious observers? Is mathematics revealing aspects of the fundamental nature of existence that evolved brains struggle to intuitively grasp? Or is there something about the mathematical approach to understanding reality that systematically emphasizes certain features while obscuring others? The disconnect runs even deeper when you consider that mathematics itself is a product of human minds. The concepts of number, equation, and proof are human inventions, developed by brains that evolved to navigate a world of medium-sized objects moving at moderate speeds in weak gravitational fields. Yet when we apply these human-invented tools to probe the foundations of reality, they consistently produce descriptions that conflict with the assumptions those same brains rely on in everyday life. Eugene Wigner, a Nobel Prize-winning physicist, called this the unreasonable effectiveness of mathematics in the natural sciences. How is it possible that abstract mathematical structures, invented by minds adapted to survive in a classical world, should turn out to be so extraordinarily successful at describing quantum and relativistic phenomena that feel completely removed from ordinary experience? Perhaps the mathematics is revealing something true about reality that our intuitions simply can't grasp. Perhaps the universe really is fundamentally mathematical in nature, and our everyday experience of solid objects and flowing time is an approximate picture constructed by brains optimized for survival rather than for fundamental understanding. Or perhaps there's something about the mathematical approach itself that creates these paradoxes. Maybe the attempt to describe reality in terms of precise quantitative relationships necessarily highlights aspects of reality that feel alien because they operate far outside the scales and conditions for which human intuition evolved. The most unsettling possibility is that both our mathematical theories and our everyday intuitions about reality are pointing toward the same conclusion from different directions. That something about the nature of existence itself is deeply counterintuitive and resists being reconciled with any simple, coherent picture of how things should be. This would mean that the feeling that something doesn't add up isn't a temporary problem that future scientific progress will solve. It would mean that the disconnect between mathematical description and intuitive understanding is a persistent feature of our encounter with reality, a sign that existence may be stranger than any mind evolved to easily comprehend. And perhaps the most unsettling part is not that we don't yet have the answer, but that the question itself keeps surviving every explanation we invent. As our measurements become more precise, a pattern begins to emerge that is difficult to ignore. The universe revealed by our most accurate instruments does not simply behave in unexpected ways. It appears to challenge the very logical principles that make measurement feel meaningful in the first place. Instead of clarifying reality, increasing precision seems to expose tensions embedded in the act of measuring itself, as though the foundations we rely on rest upon assumptions the universe does not consistently uphold. The deeper we look into the nature of measurement, the more reality seems to resist simple characterization. Not in the way a difficult problem resists solution, but in the way a basic premise about existence itself may be incomplete. Every advance in precision, every refinement of experimental technique, every expansion of observational reach seems to push us further from certainty rather than closer to it. This is not the familiar story of scientific progress, where better tools steadily reveal clearer pictures of how the world works. What we encounter instead is something more subtle and more troubling. Our instruments have become so sensitive that they have begun to reveal the limits of their own effectiveness. Our measurements have grown so exact that they now trace the boundaries of what measurement itself can reliably tell us. Consider what happens when we try to measure the position and momentum of a particle simultaneously. Classical intuition suggests this should be straightforward. An object has a location and a velocity. Better instruments should allow us to determine both properties with greater accuracy. But quantum mechanics reveals that this intuition is fundamentally mistaken. The uncertainty principle isn't a statement about the limitations of our measuring devices. It's a statement about the constraints imposed by physical theory. The mathematics tells us that position and momentum are complementary properties that cannot both be precisely defined simultaneously. Not because our instruments aren't good enough, but because the universe does not assign simultaneous definite values to both. The act of measuring one property necessarily disturbs the other in a way that's built into the formal structure of the theory. What makes this particularly unsettling is that measurement is supposed to be the foundation of objective knowledge. Science progresses by making observations, recording data, and drawing conclusions from what we can measure and quantify. But if measurement itself is limited by principles that have nothing to do with the quality of our instruments or the sophistication of our techniques, then what does that say about the interpretation of scientific knowledge? The problem becomes more acute when we realize that these measurement limits aren't confined to exotic quantum phenomena. They show up everywhere we look closely enough. General relativity reveals that the measurement of space and time depends on the gravitational field and relative motion of the observer. There's no universal reference frame from which to make objective measurements of distance or duration. What you measure depends on where you are and how you're moving relative to what you're measuring. This creates a strange situation where reality seems to be fundamentally relational. Properties don't exist independently of the process of measuring them. Space and time aren't fixed backgrounds against which events occur, but dynamic aspects of reality that change depending on how you observe them. Mass and energy aren't separate substances, but different aspects of the same underlying reality, interchangeable under the right conditions. Even more puzzling is what happens when we try to measure the vacuum itself. Empty space, according to quantum field theory, isn't empty at all. It's filled with virtual particles popping in and out of existence, with energy fluctuations that can be detected and measured. The Casimir effect demonstrates that we can actually measure the pressure exerted by these quantum fluctuations of empty space. We can build devices that are pushed together by the vacuum itself. But when physicists try to calculate the total energy density of the quantum vacuum, they get an answer that's larger than the observed energy density of the universe by a factor of 10 to the power of 120. This isn't a small discrepancy that future research might resolve. This is one of the largest known mismatches between theoretical calculation and observation. The vacuum catastrophe, as it's called, reveals something deeply challenging about the relationship between measurement and theory. Our most successful quantum field theories, the theories that allow us to calculate the magnetic moment of the electron to 12 decimal places, also predict that empty space should contain so much energy that standard cosmological models would no longer apply. The same mathematical framework that gives us the most precise predictions in all of science also gives us its largest unresolved discrepancy. This suggests that there's something about the nature of measurement itself that we fundamentally misunderstand. We assume that measurement reveals properties that objects possess independently of being measured. But quantum mechanics suggests that measurement doesn't reveal pre-existing properties. It helps define them. The act of observation doesn't just disturb the system being observed. It participates in determining what properties the system actually has. The double-slit experiment demonstrates this in the starkest possible terms. When we don't measure which slit a particle goes through, it goes through both slits simultaneously, creating an interference pattern that can only be explained if the particle interfered with itself. When we do measure which slit it goes through, the interference pattern disappears, and the particle behaves as if it went through only one slit. The counterintuitive implication is that the particle doesn't have a definite path until we measure it. The measurement doesn't reveal where the particle went. It establishes the conditions under which a path becomes well defined. Reality, at its most fundamental level, seems to be indefinite, becoming definite only through the process of measurement itself. This creates a profound puzzle about the nature of objectivity. Science is supposed to study objective reality, the way things are independent of our observations of them. But if measurement plays an active role in determining what properties objects have, then the distinction between objective and subjective begins to blur in ways that challenge the entire conceptual foundation of scientific knowledge. The measurement problem in quantum mechanics goes even deeper than the role of observation in determining outcomes. There's also the question of when and how the indefinite quantum superposition of possibilities collapses into definite classical outcomes. The mathematics of quantum mechanics describes the evolution of superposition states with perfect precision, but it provides no mechanism for the transition from superposition to definite measurement results. This is where the mathematics itself starts to reach a conceptual limit. The Schrödinger equation, which governs the evolution of quantum systems, is completely deterministic and reversible. It describes how superposition states evolve over time in a perfectly predictable way, but measurement outcomes appear to involve an irreversible collapse that isn't described by the equation. The mathematics works perfectly for describing quantum systems before measurement and for predicting the statistical outcomes of measurements, but it goes silent about the moment of transition between these two regimes. Some interpretations of quantum mechanics try to solve this by eliminating the collapse altogether. The many worlds interpretation suggests that all possible measurement outcomes actually occur, but in separate parallel universes that branch off with every quantum event. From this perspective, measurement doesn't cause collapse because there is no collapse. Every possible outcome happens somewhere in the multiverse, and we experience only one branch of a constantly branching tree of realities. But this solution comes at an enormous ontological cost. It requires accepting that an infinite number of parallel universes are constantly being created, that every possible outcome of every quantum event is equally real, and that the appearance of definite outcomes is an illusion created by our limited perspective within a single branch of the multiverse. The mathematics becomes consistent, but only by vastly expanding the conceptual picture of reality. Other interpretations try to solve the measurement problem by giving consciousness a special role in collapsing the wave function. The idea is that quantum systems remain in superposition until they interact with a conscious observer, at which point the observer's awareness somehow causes the system to assume definite properties. This preserves the objectivity of quantum systems while giving subjective experience a fundamental role in determining objective reality. But this approach raises as many questions as it answers. How does consciousness interact with quantum systems? What counts as conscious observation? Does it require human consciousness, or would any sufficiently complex information processing system work? The interpretation preserves the mathematical consistency of quantum mechanics, but only by introducing consciousness as a theoretically unresolved element within the physical framework. Perhaps the most radical interpretation is that there is no measurement problem because there are no definite measurement outcomes. The consistent history's interpretation suggests that what we think of as definite outcomes are actually just consistent stories we can tell about quantum systems. The particle didn't really go through one slit or the other. It's just that we can construct a consistent narrative in which it went through the left slit, and another consistent narrative in which it went through the right slit, but we can't construct a consistent narrative in which it went through both. This interpretation dissolves the measurement problem by dissolving the assumption that measurement reveals objective facts about reality. Instead of assuming that measurement determines which of many possible outcomes actually occurred, the interpretation suggests that measurement simply selects which of many possible stories we tell about what occurred. Reality itself doesn't contain definite facts waiting to be discovered. It contains the raw material for constructing consistent narratives, and measurement is the process by which we select which narrative to adopt. But if measurement doesn't reveal objective facts about reality, then what is science actually doing? If our most precise measurements don't tell us what's really happening in the world, but only help us select consistent stories to tell about our observations, then the entire enterprise of scientific knowledge begins to look more like a structured interpretive framework than objective truth. The crisis of measurement extends beyond quantum mechanics into other areas of physics where precision reveals paradox rather than clarity. In thermodynamics, the attempt to measure entropy at the molecular level leads to the paradox of Maxwell's demon, where perfect measurement would allow the violation of the second law of thermodynamics. The demon could sort fast and slow molecules, creating temperature differences without doing work, seemingly enabling a perpetual process through perfect measurement. But more detailed analysis reveals that the act of measurement itself must increase entropy by at least as much as the demon's sorting decreases it. The measurement process consumes energy and generates heat, ensuring that the second law of thermodynamics is preserved. The attempt to use perfect measurement to violate thermodynamics fails because measurement itself is a thermodynamic process that must obey the same laws it might seem to circumvent. This points to a general principle that emerges from the study of measurement limits. Every attempt to use measurement to transcend physical limits runs up against the fact that measurement itself is a physical process subject to those same limits. We can't measure the position and momentum of a particle simultaneously because the measurement apparatus must interact with the particle in ways that respect the uncertainty principle. We can't use measurement to violate thermodynamics because the measurement process itself must obey thermodynamic constraints. The limits of measurement aren't external constraints imposed by the inadequacy of our instruments. They're internal constraints that emerge from the fact that measurement is part of the physical reality it's trying to describe. The measuring device and the measured system are both part of the same physical universe, subject to the same laws and limitations. This creates a kind of recursive problem where the tools we use to understand reality are themselves part of the reality they're trying to understand. It's like trying to lift yourself by pulling on your own shoelaces. The attempt fails not because your arms aren't strong enough, but because the entire setup violates the logical requirements for the operation to succeed. In general relativity, this recursive quality of measurement becomes even more explicit. The geometry of spacetime determines how measuring instruments behave, but measuring instruments are themselves part of the matter and energy that determine the geometry of spacetime. The measurement of spacetime curvature requires instruments whose behaviour is determined by that same curvature. You can't step outside the gravitational field to measure it objectively because there is no outside. The measuring device and the measured field are part of the same unified geometric structure. This suggests that the crisis of measurement might be pointing towards something fundamental about the nature of knowledge itself. The traditional scientific picture assumes that we can, in principle, achieve objective knowledge of reality by making sufficiently precise measurements with sufficiently sophisticated instruments. But if measurement is inherently limited by the fact that the measuring device is part of the reality it's trying to measure, then perfect objectivity might be not just practically impossible, but logically incoherent. The recursive nature of measurement creates what philosophers call the problem of the criterion. To know something, we need criteria for distinguishing truth from error. But to establish those criteria, we need to already know what truth and error are. To measure reality accurately, we need instruments that we know are reliable. But to know that our instruments are reliable, we need to compare their results with reality. The circle can't be broken from the inside. This doesn't necessarily lead to skepticism about the possibility of knowledge. But it does suggest that knowledge might be fundamentally different from what we've traditionally assumed. Instead of objective truth, independent of the knower, we might have something more like intersubjective consistency among observers who share similar measuring procedures and theoretical frameworks. Science works not because it gives us access to objective reality, but because it provides reliable methods for achieving consensus among observers about what to expect from their measurements. The success of scientific prediction doesn't depend on science describing reality as it really is, but on science providing effective tools for coordinating expectations and actions among people who share scientific training and equipment. But this pragmatic view of scientific knowledge sits uneasily with the realist intuitions that motivate most scientific research. Scientists generally believe they're discovering facts about how the world really works, not just developing useful tools for coordinating human activities. The mathematical precision of scientific theories, their ability to make accurate predictions about novel phenomena, their success in guiding technological applications, all of this seems to point towards something deeper than mere social coordination. The tension between realist and pragmatist interpretations of scientific knowledge becomes particularly acute when we consider the role of mathematics in physics. The mathematical structures that describe quantum mechanics and general relativity don't just work as tools for making predictions. They exhibit a kind of abstract beauty and internal consistency that seems to point toward deep truths about the structure of reality itself. Eugene Wigner famously wrote about the unreasonable effectiveness of mathematics in the natural sciences. Why should abstract mathematical structures invented by human minds turn out to be so extraordinarily successful at describing the behaviour of physical systems? If science is just a pragmatic tool for coordinating human activities, why should the universe be mathematical at all? One possibility is that mathematics is effective because reality is fundamentally mathematical in nature. Perhaps the universe really is, as Galileo suggested, written in the language of mathematics, and our mathematical theories are successful because they're describing the actual structure of reality. From this perspective, the crisis of measurement reveals the limitations of our classical intuitions about reality, not the limitations of reality itself. But another possibility is that mathematics is effective because mathematical structures are the only kind of patterns that minds like ours can recognize and manipulate. We see mathematics in nature, not because nature is mathematical, but because mathematics is the only language we have for describing complex patterns. The crisis of measurement reveals not the mathematical structure of reality, but the mathematical structure of human cognition. This would mean that the precision of scientific prediction reflects not the precision of reality, but the precision of the mathematical tools we use to organize our experience of reality. The universe appears mathematical because we can only perceive and describe those aspects of it that can be captured in mathematical form. Everything else, the qualitative feel of experience, the meaning of consciousness, the purpose of existence, remains invisible to scientific measurement because it can't be translated into mathematical language. From this perspective, the measurement crisis reveals the boundaries of mathematical description rather than the boundaries of reality itself. We've pushed measurement to the limits of what can be mathematically described, and we've discovered that those limits are much narrower than we initially assumed. Reality extends far beyond what can be measured and calculated, but science can only access the measurable and calculable portion. But even this view faces serious challenges. If reality extends beyond what can be measured, how can we have any knowledge of those unmeasurable aspects? How can we distinguish between aspects of reality that are unmeasurable in principle and aspects that are simply beyond the reach of current measuring techniques? Without measurement, how can we avoid the trap of projecting our subjective assumptions onto objective reality? The crisis of measurement forces us to confront the possibility that the entire framework of objective knowledge might be built on assumptions that reality doesn't support. Not just the specific assumptions of classical physics, but the more fundamental assumption that reality has objective properties that can be discovered through careful measurement and rational analysis. If measurement is fundamentally limited by recursive constraints, if objectivity is not fully attainable because the observer is always part of the observed system, if mathematical description captures only a partial slice of a much richer reality, then what becomes of the scientific project itself? Does science become a useful model, a social construction, a pragmatic tool with limited claims about truth? Or does it point toward a different kind of truth, one that doesn't depend on the classical assumptions about objectivity and measurement that have guided scientific thinking for centuries? Perhaps the crisis of measurement is revealing not the failure of science, but the need for a more sophisticated understanding of what science is actually doing. Instead of assuming that science discovers objective truths about independent reality, we might need to understand science as a process of interactive knowledge building, where observers and observed systems influence one another in ways that make the classical subject-object distinction increasingly problematic. This wouldn't necessarily make science less reliable or less useful, but it would make it something fundamentally different from what we've traditionally assumed it to be. Instead of objective knowledge of independent reality, science might be better understood as shared, intersubjective knowledge of participatory reality, where the knower and the known are inseparably linked in ways that make pure objectivity theoretically unattainable, but enable forms of understanding that are richer and more nuanced than traditional objectivity could provide. The implications extend far beyond the philosophy of science. If measurement is fundamentally limited by recursive constraints, if reality is fundamentally relational rather than classically objective, if knowledge is fundamentally participatory rather than observational, then our entire understanding of what it means to know something, to be something, to exist in relationship with a world that includes other minds and other perspectives, may need to be reconsidered from the ground up. And perhaps the most unsettling part is not that we lack answers to these fundamental questions about measurement and reality, but that the questions themselves seem to sharpen and grow more paradoxical with every advance in our ability to measure and calculate the world around us. As our tools become more refined, a subtle attention comes into focus. Our most rigorous attempts to measure fundamental reality increasingly suggest that measurement is not merely a passive act of discovery. Instead, it appears to participate in the emergence of the very properties we once assumed were already there, waiting to be revealed. The distinction between observer and observed, so central to classical thinking, begins to look less like a fundamental feature of existence and more like a conceptual simplification that breaks down at sufficient precision. There is a familiar experience that hints at this shift. When you adjust the focus on a microscope, there is a moment when the image becomes perfectly sharp. But if you continue turning the dial, clarity gives way to blur. You haven't lost information. You've passed the point where the instrument can meaningfully resolve what it is meant to show. More precision no longer yields better insight. It exposes the limits of the tool itself. Modern physics appears to have reached a similar moment, though with a far more unsettling implication. Our instruments have become so sensitive that they no longer merely register the systems they observe. They increasingly register their own influence on those systems, blurring the boundary between measurement and reality in ways that challenge our most basic assumptions about what it means to observe the world at all. This isn't the familiar story of better tools revealing cleaner data. This is the story of tools becoming so precise that they've started to complicate the boundary between measurement and reality itself. And the implications extend far beyond the technical details of quantum experiments or gravitational wave detectors. They touch the very foundation of what we mean when we say we know something about the world. The problem emerges most clearly in quantum mechanics, but it's not confined there. Every time we push measurement precision to its absolute limits, we encounter the same recurring pattern. The measuring device doesn't simply detect properties that exist independently in the world. It plays a role in shaping what properties the world actually has. The thermometer doesn't just read temperature, it slightly changes the temperature of the system it's measuring. The voltmeter doesn't just measure electrical potential, it draws current and alters the circuit. The gravitational wave detector doesn't just sense spacetime curvature, it becomes part of the gravitational field it's trying to measure. In classical physics, these effects were treated as minor disturbances that could be corrected for or minimized with better technique. The assumption was that perfect measurement was possible in principle, even if practically challenging. But quantum mechanics reveals that this assumption is theoretically unsupported. The interaction between measuring device and measured system isn't an unfortunate side effect that can be eliminated with more careful engineering. It's the mechanism by which definite measurement outcomes emerge from indefinite quantum possibilities. Consider what happens when we try to measure which slit a photon passes through in a double-slit experiment. Without measurement, the photon creates an interference pattern that can only be explained if it passes through both slits simultaneously. With measurement, the interference pattern disappears, and the photon behaves as if it passed through only one slit. The measurement doesn't reveal which path the photon took. It establishes the conditions under which a specific path becomes defined. This creates a strange loop where measurement appears to be both discovering and participating in the formation of the properties it detects. The photon doesn't have a definite path until we measure it, but once we measure it, it definitely has the path we measured. The measurement outcome is both objective, anyone using the same apparatus will get the same result, and participatory, the result depends on the decision to measure and the particular way the measurement is carried out. The strangeness deepens when we realize that this participatory aspect of measurement isn't limited to exotic quantum phenomena. It shows up whenever we push measurement precision to fundamental limits. In thermodynamics, the attempt to measure entropy at the molecular level requires interacting with individual molecules in ways that change their energy states. The measurement apparatus must be thermally coupled to the system it's measuring, and this coupling necessarily increases the total entropy of the combined system. Maxwell's demon illustrates this perfectly. The demon is supposed to measure the velocities of individual molecules and use this information to sort fast and slow molecules, creating temperature differences without doing work. But more careful analysis reveals that the measurement process itself requires energy expenditure and entropy production. The demon's memory must be periodically erased to avoid infinite accumulation of information, and this erasure generates heat. The measurement process that enables the sorting also ensures that the second law of thermodynamics is preserved. The pattern repeats in general relativity. Gravitational wave detectors like LIGO must be extraordinarily sensitive to measure the tiny stretching and compression of spacetime caused by colliding black holes billions of light years away. But the detectors themselves are massive objects that create their own gravitational fields and respond to external gravitational influences. The measurement of spacetime curvature requires instruments whose behavior is determined by that same curvature. The measuring device and the measured field are part of the same unified geometric structure. This recursive quality of measurement, where the tool used to probe reality is itself part of the reality being probed, creates conceptual problems that go far beyond technical challenges. It suggests that the entire framework of objective measurement might be based on a simplified assumption. We assume we can, in principle, step outside the system we're studying and observe it from an external perspective. But if the measuring device is always part of the system, if the observer is always physically coupled to the observed, then pure objectivity becomes not just practically difficult, but conceptually limited. The crisis becomes particularly acute when we try to measure the properties of space and time themselves. Special relativity reveals that measurements of length and duration depend on the relative motion between observer and observed. There's no universal reference frame from which to make objective measurements. General relativity goes further, showing that the geometry of space-time is determined by the distribution of matter and energy, including the matter and energy of the measuring instruments themselves. This creates a situation where the act of measurement contributes to the space-time geometry that determines how the measuring instruments behave. The rulers and clocks we use to measure space and time are themselves embedded in the space and time they're measuring. Their behavior is governed by the same geometric relationships they're designed to detect. The measurement of space-time becomes a process where space-time is probed through the mediation of material instruments. The implications extend beyond physics into the philosophy of knowledge itself. The traditional scientific picture assumes that knowledge progresses by making increasingly precise measurements of objective properties that exist independently of our observations. But if measurement is inherently participatory, if the measuring device always influences what it measures in ways that can't be eliminated or fully corrected for, then what does it mean to have objective knowledge of the world? One response is to abandon the goal of objectivity altogether and embrace a purely subjective or relativistic view of knowledge. From this perspective, there are no objective facts about reality, only different perspectives and interpretations that depend on the observer's position, instruments, and theoretical commitments. Science becomes a social construction, a way of organizing human experience rather than a method for discovering mind-independent structure. But this response seems to go too far in the opposite direction. The mathematical precision of physical theories, their success in making accurate predictions about novel phenomena, their effectiveness in guiding technological applications, all of this suggests that science is discovering robust structural regularities about the world, not just constructing useful fictions. A more nuanced response recognizes that measurement is participatory without concluding that knowledge is purely subjective. Instead of assuming that observers and observed systems are completely separate, we might understand measurement as a process of interaction between systems that are always already physically interconnected in complex ways. Knowledge emerges from these interactions not as a passive reflection of pre-existing properties, but as an active process of mutual specification between knower and known. This participatory view of knowledge doesn't eliminate objectivity, but relocates it. Instead of objectivity residing in the independence of observed properties from the observer, it resides in the reproducibility and coherence of measurement outcomes across different observers using similar methods. The objectivity of science lies not in its ability to transcend the participatory nature of measurement, but in its ability to coordinate and systematize participatory knowledge creation processes. From this perspective, the mathematical structures of physical theory don't describe reality as it exists independently of measurement. They describe the patterns that emerge from measurement interactions themselves. The equations of quantum mechanics don't tell us what quantum systems are like when nobody is looking. They tell us what kinds of measurement outcomes to expect when we look in particular ways. The field equations of general relativity don't describe the intrinsic geometry of spacetime. They describe how spacetime geometry responds to the presence of matter and energy, including the matter and energy of measuring instruments. This participatory understanding of measurement helps explain why mathematics is so extraordinarily effective in describing physical phenomena. Mathematical structures aren't effective because reality is intrinsically mathematical. They're effective because measurement interactions naturally generate mathematical patterns, and mathematical tools are precisely designed to detect and manipulate such patterns. The universe appears mathematical because mathematics is the language of measurement interactions, not because mathematics is the intrinsic language of reality itself. But this raises new questions about the relationship between measurement and consciousness. If measurement is participatory, if it involves genuine interaction between measuring device and measured system, then what role does conscious observation play in this process? Does consciousness have special properties that distinguish it from other measuring devices, or is consciousness simply one type of complex measuring system among others? Some interpretations of quantum mechanics assign consciousness a special role in collapsing the wave function and determining definite measurement outcomes. The idea is that quantum systems remain in indefinite superposition until they interact with conscious observers, at which point the observer's awareness causes the systems to assume definite properties. This preserves the participatory nature of measurement while giving subjective experience a fundamental role in objective reality. But this consciousness-based interpretation faces serious conceptual challenges. How does consciousness interact with quantum systems? What counts as conscious observation? Does it require human consciousness, or would any sufficiently complex information processing system work? And why would consciousness have this special power when other physical processes don't? Alternative interpretations avoid giving consciousness a special role by treating all measurement interactions on equal footing. From this perspective, consciousness is one type of complex physical process that can participate in measurement interactions, but it doesn't have fundamentally different properties from other measuring devices. The participatory nature of measurement emerges from the physics of interaction itself, not from any special properties of conscious observers. This democratic view of measurement avoids the conceptual problems of consciousness-based interpretations, but it raises its own questions about the nature of definite outcomes. If all physical interactions are measurement-like, if every collision between particles involves mutual influence and mutual specification of properties, then why don't we observe superposition effects in macroscopic systems? Why does the classical world of definite properties emerge from quantum interactions that seem to involve continuous mutual influence and specification? The answer involves understanding how measurement interactions scale up from microscopic to macroscopic systems. Individual quantum interactions do involve mutual influence and mutual specification of properties, but when many such interactions occur simultaneously, the overall effect is to suppress superposition and generate classical behavior. This process, called decoherence, doesn't require conscious observation or special measuring devices. It emerges naturally from the complexity of multi-particle interactions in realistic environments. Decoherence explains why quantum superposition effects are typically confined to carefully isolated microscopic systems, while macroscopic systems exhibit classical behavior. It's not that macroscopic systems are intrinsically classical, it's that they interact with their environments in ways that make quantum superposition effects extremely difficult to observe. The measurement problem isn't solved by decoherence, but it's reframed. Instead of asking why wave functions collapse during measurement, we ask why certain types of measurement interactions preserve quantum superposition while others suppress it. This brings us back to the recursive nature of measurement. Decoherence theory treats measurement interactions as physical processes that can be described using the same mathematical formalism that describes the systems being measured. The measuring device and the measured system are both quantum mechanical systems, and their interaction can be analysed using quantum mechanical principles. But this analysis requires taking a perspective that encompasses both the measuring device and the measured system, treating them as parts of a larger quantum mechanical system. This larger perspective reveals that measurement doesn't eliminate the participatory nature of quantum interactions. It redistributes it. The measuring device and measured system don't interact as separate classical objects. They become entangled as parts of a larger quantum system, and the measurement outcomes emerge from the structure of this entangled system. The participatory nature of measurement is preserved but relocated to the level of the combined system. But this relocation creates a new version of the same conceptual problem. To understand the measurement interaction between device and system, we need to take a perspective that encompasses both. But this perspective requires its own measuring instruments and theoretical frameworks, which are themselves part of the reality they're trying to describe. The recursive structure of measurement can't be eliminated by moving to higher levels of analysis. It reappears at every level. This suggests that the participatory nature of measurement might be a fundamental feature of reality rather than a technical problem to be solved. Instead of trying to eliminate the influence of measuring devices on measured systems, we might need to accept that measurement is inherently relational. Properties don't exist as intrinsic features of isolated systems. They emerge from relationships between systems, including the relationships involved in measurement interactions. From this relational perspective, the question isn't how to eliminate the influence of measurement on reality. The question is how to understand reality as the pattern of relationships that includes measurement interactions as fundamental constituents. The measuring device doesn't disturb a pre-existing reality. It participates in the ongoing process by which reality takes on determinate structure through relational interactions. This relational understanding of reality has profound implications for how we think about scientific knowledge. Instead of assuming that science discovers objective properties of independent reality, we might understand science as a process of participating in reality's ongoing structural articulation. Scientific theories don't describe what the world is like independently of our involvement with it. They describe patterns in the ways the world responds to our methods of engagement with it. This doesn't make scientific knowledge less reliable or less valuable, but it does make it something fundamentally different from what we traditionally assumed it to be. Instead of passive reflection of independent reality, scientific knowledge becomes active participation in reality's continuous becoming. Instead of objective truth about subjective experience, it becomes intersubjective coordination of participatory processes. The crisis of measurement reveals that the distinction between objective and subjective, between observer and observed, between knower and known, might be conceptual artifacts that lose coherence when pushed to fundamental limits. Reality might be neither purely objective nor purely subjective, but relational in ways that transcend these traditional categories. If measurement is inherently participatory, if knowledge is inherently relational, if reality is continuously specifying itself through interactions that include our methods of engaging with it, then the entire framework of classical epistemology needs to be reconsidered. The goal isn't to eliminate human involvement in knowledge creation, but to understand how human involvement contributes to reality's ongoing self-specification. This participatory understanding doesn't lead to relativism or subjectivism. The patterns that emerge from measurement interactions are real and objective, even if they don't exist independently of the interactions that generate them. The mathematical structures of physical theory are discovered, not invented, even if what they describe are relational patterns rather than intrinsic properties of isolated systems. And perhaps the most unsettling part is not that measurement is participatory, but that the more precisely we measure, the more clearly we see that the boundary between measurement and reality was always a conceptual boundary we created to make the deep uncertainty of existence feel manageable. At the deepest levels of inquiry, another discomfort quietly emerges. The very mathematical precision required to describe reality at its most fundamental scale seems to generate results that strain the logical consistency mathematics itself depends on. The frameworks that allow us to describe the world with extraordinary accuracy begin, under sufficient pressure, to produce internal tensions and apparent paradoxes, subtle signs that mathematical description may be approaching the limits of what it can meaningfully contain. This is unsettling precisely because of how deeply we trust mathematics. We rely on it in the same way we rely on the ground beneath our feet. When you calculate the trajectory of a projectile, balance a checkbook, or measure the dimensions of a room, the numbers behave exactly as expected. 2 plus 2 equals 4, whether you're counting apples or atoms. The Pythagorean theorem holds for triangles sketched on paper, and for the geometric relationships between distant stars. This reliability doesn't merely feel useful, it feels foundational, like a direct expression of how reality itself is structured. And yet, when that same mathematical discipline is pushed to describe reality at its most fundamental level, something begins to feel subtly unstable. But when physicists push mathematical description to its absolute limits, when they try to use mathematics to describe reality at its most fundamental level, something strange happens. The mathematics doesn't just become difficult or counterintuitive, it begins to produce results that challenge the internal expectations of logical consistency that mathematics itself relies on. And that's where things quietly become uncomfortable. The first hint that mathematics might be approaching its limits appears in quantum field theory, our most successful description of particles and forces. The theory makes predictions that have been confirmed to extraordinary precision. Calculations of the magnetic moment of the electron agree with experiment to 12 decimal places, a level of accuracy comparable to measuring the distance between New York and Los Angeles to within the width of a human hair. But when physicists try to calculate certain properties of the quantum vacuum, the supposedly empty space between particles, the mathematics produces formally divergent results. Not just very large numbers, but expressions that mathematically diverge toward infinity. The energy density of empty space, according to the raw calculations, comes out far beyond physically observed values. This isn't a technical problem that better computational methods might solve. It's a breakdown where the mathematical formalism ceases to yield physically meaningful answers without additional procedures. The standard response is a procedure called renormalization, where physicists essentially subtract one infinity from another to obtain finite, measurable results. The procedure works. It allows the theory to make those spectacularly accurate predictions. But it can feel like mathematical sleight of hand, a way of making the divergences manageable without fully understanding why they arise in the first place. The deeper you look into renormalization, the more conceptually unsettling it becomes. The procedure requires making choices about how to handle the divergences, choices that affect the final results in ways that seem to depart from naive expectations of strict determinism in mathematical calculation. Two mathematicians following the same logical steps should arrive at the same answer, but in renormalization, the answer depends on convention-dependent regularization schemes. This suggests that the mathematical description of reality at the quantum level isn't just technically challenging. It may involve formal structures that stretch traditional notions of mathematical rigor. The most precise physical theory we've ever developed works because we've learned how to systematically manage certain divergences that arise at its foundation. The problem becomes more acute when you try to extend quantum field theory to include gravity. General relativity describes gravity as the curvature of spacetime itself, and when you try to apply quantum mechanical principles to this curved geometry, the mathematics becomes even more pathological. The divergences multiply and become uncontrollable. No known renormalization procedure successfully resolves them. For nearly a century, physicists have been trying to develop a theory of quantum gravity that would resolve these mathematical tensions. String theory, loop quantum gravity, causal set theory, each approach requires mathematical concepts so abstract that they stretch the notion of calculation to its limits. Some versions of string theory require the existence of additional spatial dimensions that we cannot currently observe. Others suggest that space and time themselves may be emergent properties of something more fundamental that can only be described using mathematical structures that resist geometric intuition. But even these exotic approaches haven't eliminated the underlying difficulty. They've pushed the mathematical challenges to deeper levels. String theory, for instance, requires mathematical consistency conditions that can only be satisfied under very specific circumstances, particular numbers of dimensions, particular symmetries, particular field configurations. The mathematics itself appears to constrain which physical models are internally consistent, but the relationship between these mathematical constraints and empirical reality remains unresolved. This creates a profound puzzle about the nature of mathematical truth itself. We usually think of mathematics as a tool for describing reality, but in fundamental physics, mathematics seems to be constraining what realities are even theoretically admissible. The mathematical formalism isn't just describing what happens to exist, it limits what can be consistently modelled. But if mathematics is a human-constructed formal system, developed by minds adapted to navigate a classical world, why should mathematical consistency place such strong constraints on the structure of physical reality? The puzzle deepens when you consider that these mathematical tensions aren't isolated technical issues. They seem to point toward fundamental limits in the capacity of mathematical reasoning to provide complete descriptions of any sufficiently complex system. Kurt Gödel proved in 1931 that any mathematical system powerful enough to include arithmetic will contain statements that are true but unprovable within the system. Every mathematical framework has inherent blind spots, truths that cannot be derived using its own rules. Gödel's incompleteness theorems are often treated as abstract results in mathematical logic, but they carry implications for physics as well. If the mathematical frameworks used to describe reality are necessarily incomplete, then there will always be aspects of physical reality that resist complete mathematical capture. The equations may be extraordinarily accurate within their domains, but they cannot provide exhaustive descriptions of the systems they model. This incompleteness isn't a temporary limitation of current methods, it's a structural feature of mathematical reasoning itself. No matter how advanced our mathematical tools become, there will always be questions that lie beyond what those tools can formally resolve. Mathematical description is inherently partial, but the difficulties go beyond incompleteness. In some areas of fundamental physics, the mathematics doesn't merely leave questions unanswered, it generates formal tensions that challenge the internal coherence of the framework itself. Consider the measurement problem in quantum mechanics. The Schrödinger equation describes quantum evolution with precise mathematical clarity. It is deterministic and reversible, but measurement outcomes appear to involve irreversible transitions that the equation itself does not describe. The same mathematical framework demands both smooth, continuous evolution and abrupt, discontinuous outcome selection. This is not simply a missing piece. It reflects a formal tension within the theory. The mathematics must accommodate deterministic evolution and probabilistic outcomes, reversible dynamics, and irreversible events within a single conceptual structure. Interpretations of quantum mechanics attempt to address this tension in different ways. The many worlds interpretation preserves formal consistency by expanding the ontology. Copenhagen-style approaches accept the formal limitation and treat measurement as a primitive. Consciousness-based approaches introduce non-formal elements. Each route resolves some aspects while placing strain on others. Similar structural tensions arise in general relativity. Singularities represent points where the mathematical description ceases to apply. At black hole centers or at the earliest moments of cosmic evolution, curvature diverges and equations lose predictive power. These are not merely gaps in data, they are boundaries where the formalism acknowledges its own limits. For decades, new theoretical frameworks have been proposed to address these issues. Yet each attempt replaces one class of mathematical difficulties with another. The challenges shift, but they persist. This recurring pattern suggests that these mathematical tensions may not be temporary obstacles. They may be indicators of the inherent limits of mathematical description when applied to the deepest layers of reality. This does not diminish mathematics. On the contrary, the extraordinary successes of modern physics demonstrate the remarkable reach of mathematical reasoning, but they also reveal where that reach ends. Perhaps the discomfort arises from an assumption we rarely question, that complete mathematical description of reality is possible in principle. The internal tensions at the foundations of physics suggest this assumption may itself be flawed. If so, then the sense that something doesn't add up is not evidence of failure. It may be evidence that we are encountering the natural boundaries of formal reasoning. This would imply that future progress may not consist solely of more comprehensive mathematical frameworks, but of learning how to work responsibly with formalisms that are necessarily incomplete and context-dependent. Such a shift would have implications beyond physics. Any field relying on mathematical modelling would need to reconsider the scope and limits of what models can legitimately claim. It would also reshape how we understand rationality itself. If reality cannot be fully captured by logically complete systems, then rational understanding may involve navigating uncertainty and formal limitation rather than eliminating them. This does not mean abandoning reason. It means recognizing that reason may operate most effectively when it acknowledges its own boundaries. And perhaps the most unsettling part is not that something about reality isn't adding up, but that this failure to add up may be the clearest signal mathematics has ever given us about the true complexity of existence itself.